In this lesson, we'll learn a new technique of integration known as trigonometric substitution. So when it comes to integration involving square roots, we are very limited in the types of functions that we're able to integrate. And we definitely saw this when we were learning about the process of calculating arc length. So here are a few types of integrals that we are able to calculate when square roots are involved, and we'll see what we can then learn how to do next. So just as a refresher, one type of integral that we can use when square roots are involved is a use of the power rule. So for instance, like this particular example, I could rewrite as, instead of 1 over the square root of x, of course, the square root of x could be written as x to the 1/2 power. And if I made that a negative 1/2 power, I could rewrite this in such a way that the power rule would apply. So x to the negative 1/2 power, what I would need to do is add 1 to that exponent. So x to the positive 1/2 power over 1/2 plus our arbitrary constant c gives us 2 square root of x plus c. Okay. The next type of integrals that we learned how to work with that involved square roots were problems that use substitution would work. So for instance, if I noticed here that the power underneath, or the power of this polynomial underneath the square root is 1 more than the power of the polynomial in the numerator, I can take advantage of that and just let u be x cubed minus 4, so that du would be 3x squared dx. And I have a multiplier of 3, which of course I can handle by just dividing both sides of this expression by the 3, and then I can substitute directly for x squared times dx with 1/3 du. So this could be rewritten as 1/3 times the integral. So x squared dx gets replaced with du, and then this becomes 1 over u. And now we essentially have the same problem as before. We'll change this into 1/3 times the integral of u to the negative 1/2 power. And when we integrate, it will still look the same as the previous example. So u to the 1/2 over 1/2 plus c. We just have to remember in the end to go back to the original variable. So taking care of these constants, that will become 2/3. And then u to the 1/2 would become the square root of u being x cubed minus 4 plus c. Okay, that's another way that we could solve integrals involving square roots. Another way is what we learned with inverse trig functions. So with inverse trig functions, we saw a few special cases, and these didn't apply very often, but when they did, it was pretty straightforward, as long as you remember the formula. So this form right here, 1 over the square root of 4 minus x squared. If we assume 4 could represent some variable a, which of course this has to be a squared, so like a would actually just be 2, so that 2 squared would be 4. And similarly, this right here could be some function u, but I would need the square of u to work with. All right, and then the formula says that this particular setup, when it's a constant minus x squared, that's our arc sine, and so it is officially arc sine of u over a. U is x, a is 2, plus c. And that's kind of an interesting one because we didn't really, or you may not have really seen exactly why that is. We'll actually learn that today. So I'll make sure to do an example which explains those inverse trig functions. So we'll come back to that one a little bit. Then next up was another technique, and you may or may not have seen this, but this is called back substitution, And this is kind of an advanced technique of a use of U substitution. So if you'll notice, in the previous example that I used U substitution, I looked at the power of the polynomial under the root and noticed that it was one more than the power of the polynomial outside of the root. And that allowed me to use U substitution. Here, that's not the case. These are both degree 1 polynomials. But it's actually okay here, and I can use U substitution. I'll show you why. Because if I let U be the part under the radical, then du becomes dx, of course. But this right here, this is just a function, and you're allowed to manipulate functions as you want. And it's not common, but you really can take this and solve it for x. And so you could say x is equal to u minus 1. And again, that's not common, but it is a valid technique. And it actually gives us something to substitute the variable x with. I just change it into u minus 1. And then you can actually think about the same thing underneath this radical. If you made x into u minus 1, then you would have 1 plus u minus 1. The ones would cancel, and essentially you just have the square root of u, or it's generally a little bit better to go ahead and express that as its equivalent 1/2 power. But that allows me to substitute everything so that it's a function entirely of u. And if I distribute u to the 1/2 power, that would be u to the 3/2 minus u to the 1/2 du, for which I can integrate, and that would be adding 1 to 3/2 would be 5/2, so u to the 5/2 over 5/2 minus u to the 3/2 over 3/2 plus c. And that essentially gets me to 2/5. U, its definition was 1 plus x, so I'll go ahead and replace that back. So 1 plus x to the 5/2 power minus 2/3 times 1 plus x to the 3/2 power. And that gets us our integral. But all of these techniques don't really apply to just any problem with the square root in general. It would really have to be something that is something that's going to fall into one of these specific categories. And the technique that we learned today isn't really going to broaden the ability for us to evaluate any square root either, but it will add some additional possibilities to us. So the times when the method we're going to learn today will apply, or when we have parts of the problem that look like the square root of a squared minus x squared, the square root of a squared plus x squared, or the square root of x squared minus a squared. And these can, in fact, not involve roots. This can apply if you just have a difference of squares or a sum of squares, or if it's like a 3/2 power or something of those forms. These can still apply. It's just generally we're looking for the square roots that kind of indicate that these techniques might apply. So let's take a look at what this is and how it would work. So we have this first example here. We have an integral 1 divided by the square root of 9 plus x squared dx. Now, there's a lot going on here, and I could give you a step-by-step process, and I will, but for now I want you to kind of just follow through and watch how I go through this process, because the process is a bit daunting for students at first. So I'd like for you to just watch it for a moment before I describe steps and that sort of thing. Now, here's the intuition. This part right here, this 9 plus x squared, this looks like a Pythagorean identity. Pythagorean identity. Okay, and what I mean by that is the Pythagorean identity, of course, is a squared plus b squared equals c squared. And so you have the sum of two squares, or if you rewrote this, you could have b squared equals c squared minus a squared, so the difference of squares could work as well. But it looks like a Pythagorean identity. And the cool thing about the Pythagorean identity is you could take the sum of two squareds and replace them possibly with just one thing that's squared. And if you can do that, then you would be taking the square root of something that is squared, which would just be what's under that radical. And that would be a whole lot easier to integrate than the original. So that's kind of what we're working toward here. Now, how do we get there? Well, here's what we have to do. So if we're working with Pythagorean identities, you need to go back to some right triangle trigonometry. So our right triangle trigonometry, it's not the difficult stuff, it's just the basic stuff. So if you remember your friend SOHCAHTOA, for instance, that's really enough to do this. SOHCAHTOA is just that acronym that is the relationship of sides of a triangle based off of each trig function. So sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and so forth. Okay, so if I were to set up a right triangle, okay, because the Pythagorean identity is involved, then right triangles are inherently involved here because the Pythagorean identity works with measuring the sides of right triangles. Now, in order to work with a triangle, you probably need an angle measured that's observed. So we'll just call one angle theta. Of course, not the 90-degree one. And then we have to make note of how to measure sides of a triangle. All right, so if you'll recall from the example using the arcsine function, I took the constant term, used its square root, and I took the function x squared and used its square root as u and a. We're kind of doing the same thing here. All right, but if I take those values and basically say that a is equal to 3 and u is equal to x in the same way. So this is square root of 9 and square root of x. Square root of x squared, that is. And that I can think of as two sides of this triangle. Okay, so for instance, if I let this side be 3 and this side be x, then what I could notice is that the tangent of my angle theta would be x over 3. Okay, all right. So that's actually a key thing here. And I'll go into details about this a bit later, but that is really kind of a key thing. Now, if these are two sides of a triangle, I can determine the third using the Pythagorean identity. So what I'll do is I'll just say, for right now, let's just say it's A, and I can say, well, I guess C is probably the better variable there. I can say C squared is equal to x squared plus 3 squared, or C would be the square root of x squared plus 9. So this length right here is the square root of x squared plus 9. And that's interesting because that is, in fact, a part of my integral, the square root of 9 plus x squared, but that's the same thing. Now, here's what I can do with that. I can actually say here that this integral, so I apologize for all the arrows, but I can say that this integral is equal to, say for instance, 1 over, I could call this c, but I don't know if that's entirely useful because I'd like to make it something relative to either x or theta. Let's see how we could make it relative to theta. So the easiest way to make that relative to theta is I could say here, all right, so I've got a constant on this side, and this is my hypotenuse. So this would be the adjacent side to theta, and this would, of course, be the hypotenuse. So the adjacent and the hypotenuse are related through cosine. So I could actually say here, the cosine of theta is equal to that adjacent side divided by the hypotenuse. And that's just basic right triangle trigonometry. And what's really cool about that is what it allows me to do is actually substitute even better here. I've got this constant 3, but you can always divide constants over, and let's make this 1/3 instead. So I can say 1/3 cosine theta is exactly this. So this would just replace as 1/3 cosine theta. So all of this gets replaced with this. Okay? Now, dx. What's going on with dx? So I can't integrate something in terms of theta dx. It doesn't make any sense anymore. So I actually have to have something in terms of d theta. How do I change this into a d theta? Well, I do have a clue, and I really apologize for all the arrows here, but I have a clue right here. And it tells me, since tangent to theta is x/3, that I could take the derivative of both sides, and I could say the derivative of tangent, so is secant squared theta d theta. And then I would just take the derivative of this side as well. So the derivative of x/3 would be 1/3 dx. Okay, and you might be thinking, like, why are you doing this? Okay, remember your u substitution. Let me do a different color so that this isn't part of the problem. When you define something for u substitution, the next step you do is come up with a definition for du. We're effectively doing the same thing. But just think of my substitution here as kind of like, let's say 3 tan theta equals x. And then we're differentiating both sides. So that would be 3 secant squared theta d theta equals dx. So to substitute for dx, I actually do need to use exactly 3 secant squared theta d theta equals dx. Okay, so now I also have something to replace for dx. It becomes 3 secant squared theta d theta. All right, so at this point, there's some things I can simplify. Clearly, 3 and 1/3. That's no problem. But also, if I have cosine theta, and I recall that secant is just the same thing as 1/, cosine squared theta, I actually can cancel out one of these factors with this one, leaving me with effectively 1/, cosine, which is the same thing as secant theta d theta. Okay, if you're still with me, we're actually almost done here. Now, to recap what I've done so far, I have used Pythagorean identity in order to change the form of this equation into something in terms of theta rather than the variable x. And it's all based off this triangle right here. This simplification is just your basic trigonometry. And at this point, we know what the integral of secant theta is. The integral of secant theta is the natural log of the absolute value of secant theta plus tangent theta. And we have one last thing to do. So now we have everything written in terms of theta for our answer, because this is our integral, the function that is our integral, but it's in terms of theta. We need to get it back to x. And that's where this triangle comes into play again. So secant theta. Secant is the inverse of cosine, and cosine is adjacent over the hypotenuse. So secant is actually the hypotenuse over the adjacent side. So this would be the square root of x squared plus 9 over 3. And then tangent is the opposite over the adjacent side. So the opposite side is x, the adjacent is 3, so x over 3 plus c. And there we have it. That's our final answer for this integral. Now, if you read through the text, you'll see the text will often skip these steps of the triangle. And you might think that there's an advantage there. I don't really think there is, because number one, you have to go back to the triangle in the end in order to rewrite your expression in terms of the variable x. So you're going to need that triangle at some point anyway. What they do is they have a way of determining what the substitution should be based off of if you're got a constant plus x squared, or it's a constant minus x squared, or if it's a x squared minus the constant. And that leads you to a substitution. Like, for instance, it would lead you to x equals 3 tangent theta. So here's what they would have done. And I'm just going to do this in a different color so you can see it. So an alternate method. They have the integral of 1 over 9 plus x squared dx. And then they give you the substitution of, or they give you a method of arriving at the substitution should be x equals tangent theta, 3 tangent theta because of that variable a. So 3 tangent theta. And then they say to get dx, so you would have 3 secant squared theta, d theta. And they say to just substitute these directly into your integral. So you would have the square root of 1 plus the square root of, or sorry, the integral of 1 over the square root of 9 plus x is going to be 3 tangent theta squared. And then d theta, or dx, becomes 3 secant squared theta d theta. And it is absolutely true that this will all simplify right down to this step right here. But it sort of maximizes the need for trigonometric reduction and algebraic reductions to make this happen. I really don't prefer this method much at all. Just so you can see it, it would basically look like this. Let me work on this part here first. So 9 plus, this would become 9 tangent squared theta, which would be 9 times 1 plus tangent squared theta, which you should remember as a Pythagorean identity as 9 secant squared theta. Okay, now all that's underneath a square root. So 1 over the square root of this 9 secant squared theta. Notice that this is all perfect squares now. Becomes 1 over 3 secant theta. Okay, so then you have all of this just becoming 1 over 3 secant theta. So your integral then becomes 1 over 3 secant theta times 3 secant squared theta d theta. The 3's cancel just like before. Secant goes into secant squared, and we're right at where we were before. So secant theta d theta. You can do it that way. It will work every single time. Or you can use the triangle to do the substitution, whatever works best for you. I will use the triangle because I like that method better, but you can absolutely use the method the book shows as well. Now, in order to do this in general, anytime you have an integral involving the square root of a squared plus x squared, then what you're going to do is you're going to let x equal a tan theta. And as I showed right through here, this is effectively going to yield, when you make your substitutions and reduce, it will turn out to be a secant theta. All right. And then you have dx as a secant squared because that's going to be the derivative of x. Then once you get to that point, simplify your expression as much as possible. You may have to use some trig identities. Sometimes you do, sometimes you don't. Evaluate the resulting integral, and then use your reference triangle to rewrite in terms of x. So the individual steps here that I used, you have an initial substitution that you're going to use, and it involves the initial substitution and determining the value dx. Once you make those substitutions, you can either use the triangle or these substitutions directly to plug into your integral in order to reduce it. So this would be step 2 down to this point right here. Then you'll actually do the integration. So that's step 3. And lastly, replace back for the original variable. Those are the 4 steps that you'll always do for trigonometric substitution integrals. Occasionally, you may have to use some trig identities when you're substituting back. Sometimes you have to use arc trig functions. We'll do some different examples and I'll show you all the possibilities, but just know that it might get a little bit more involved in that last step sometimes.